In this lesson, we will examine the free particle problem. This is essentially the particle in a one-dimensional box problem, but with a potential energy equal to zero everywhere. Let's solve the time-independent Schrödinger equation for a free particle. In general, the time-independent Schrödinger equation is h hat psi equals E times psi, where h hat is the Hamiltonian operator and E is the energy. For a one-particle system confined to move on just the x-axis, the Hamiltonian operator is the kinetic energy operator, which takes the second derivative with respect to x, then multiplies by negative h bar squared over twice the mass, plus the potential energy operator v. For the free particle, the potential energy is zero everywhere, so the Schrödinger equation simplifies to negative h bar squared over 2m times the second derivative of psi with respect to x is equal to E times psi. We have seen the second-order differential equation before. It's the same one for the particle in a box, except that now it is applicable everywhere, that is, from x equals negative infinity to x equals positive infinity. And we have already shown that the general solution to this differential equation can be written as follows. The wave function psi is equal to c1 times e to the ikx plus c2 times e to the negative ikx, where c1 and c2 are constants, and k is equal to the square root of 2me divided by h bar. Rearranging this equation, we can solve for E as k squared times h bar squared divided by 2m. Unlike the particle in a box problem, we don't have boundary conditions for a free particle, which would allow us to put restrictions on the constants c1, c2, and k. Recall that for a particle in a box, the condition that psi must be equal to 0 at x equals 0 requires that c1 plus c2 be equal to 0, which simplifies the expression for psi to some constant a times the sine of kx. The condition that psi must be equal to 0 at x equals L requires that the constant k must be equal to a multiple of pi over L. This led to the quantization of energy. Finally, the normalization condition that the particle is to be found between x equals 0 and x equals L meant that the absolute value of A is square root of 2 over L. For a free particle, these restrictions are no longer applicable. So what do we do now? Let's just look at specific solutions by making some assumptions about C1 and C2. Let's see where it leads us. What if C2 is equal to 0? Well, that would make this term equal to 0. So psi will just be equal to C1 times e to the ikx. Let's apply the momentum operator P sub x hat on psi. This means take the derivative of psi with respect to x, then multiply by h bar over I. Substituting c1 times e to the ikx for psi, we get h bar k times c1 times e to the ikx, or h bar k times psi. In other words, psi is an eigenfunction of the momentum operator. What is the eigenvalue? The eigenvalue is h bar k. Since k is positive, the momentum h bar k is positive. This means the wave function of c1 times e to the ikx describes a particle that is moving in the positive x direction, and the magnitude of the momentum is equal to h bar times k. Note that since the momentum is h bar squared times k squared is p sub x squared. To summarize, if psi is equal to c1 times e to the ikx, we can say that the particle has a well-defined momentum and energy. What about the probability density function? The probability density function is psi star times psi. It should be quite easy to show it is equal to a constant. Specifically, it is equal to the square of the absolute value of c1. What does this mean? This means that the probability of finding the particle is uniform from negative infinity to infinity. This is consistent with the uncertainty principle, since this particular state has a well-defined momentum. We know how fast the particle is moving and in which direction. But we have absolutely no idea where the particle is going to be if we try to locate it. Note that this doesn't mean that psi is constant. Recall that we can write e to the ikx as cosine kx plus I times sine kx. We can see that the real and imaginary parts of psi oscillate sinusoidally as x goes to positive and negative infinity. Note that the wave function in this particular case is not normalizable. How about the case where C1 is equal to 0? That would mean that this term is equal to 0. So psi will just be equal to C2 times e to the minus ikx. What do we get if we apply the momentum operator p sub x hat on psi? We get back psi times negative h bar k. In other words, psi is an eigenfunction of the momentum operator. But this time, the eigenvalue is negative h bar k. Since k is positive, the momentum, negative h bar k, is negative. This means the wave function c2 times e to the minus ikx describes a particle that is moving in the negative x direction, and the magnitude of the momentum is equal to h bar times k. The particle has a well-defined momentum. Of course, since psi is an eigenfunction of the Hamiltonian operator, it also has a well-defined energy. Note that the square of negative h bar times k is also k squared times h bar squared. As for probability density, it's easy to show that it's constant and is equal to the square of the absolute value of C2. Again, we see the uncertainty principle demonstrated here. Since the momentum is well defined, we completely lose information about the location of the particle. The probability density for locating the particle is uniform from x equals negative infinity to x equals positive infinity. Let's take a look at the case where C1 is equal to C2. In this case, we can factor out C1, and we can write psi as C1 times the sum of e to the ikx and e to the negative ikx. Recall Euler's formula. E to the ix is equal to cosine x plus I sine x, and e to the negative ix is equal to cosine x minus I sine x. It's easy to show that psi can be written as 2 times c1 times cosine of kx. What happens if we apply the momentum operator on psi? We take the derivative of psi with respect to x, then multiply by h bar over I. We get h bar over I times 2 times c1 times negative k times sine of kx. We can see that we do not get back psi times a constant. So in this case, psi is not an eigenfunction of the momentum operator. The momentum of the particle is not well defined. Let's see why the momentum is not well defined. Let's apply the momentum operator on e to the ikx. By now, you should be easily able to show that e to the ikx is an eigenfunction of the momentum operator with an eigenvalue of h bar k. Similarly, if we apply the momentum operator on e to the negative ikx, we can show that e to the negative ikx is also an eigenfunction of the momentum operator with a value of negative h bar k. Therefore, we can see that psi is a linear combination of two non-degenerate eigenfunctions of the momentum operator. It's a linear combination of e to the ikx, which has an eigenvalue of h bar k, and e to the negative ikx, which has an eigenvalue of negative h bar k. Psi itself is not an eigenfunction of the momentum operator. It's the direction that is not well defined. Since the magnitude is well defined, the square of the magnitude is also well defined. The square of the magnitude is h bar squared times k squared. So we can also write the energy as the square of the magnitude of the momentum over 2 times the mass. Let's see what the expectation value of the momentum is. To get the expectation value, we apply the operator on psi, multiply by the complex conjugate of psi, then integrate over all space. Plugging in 2c1 cosine kx for psi and simplifying, we get this expression. If we examine this integral, we can see that the integrand cosine kx times sine kx is an odd function. We are integrating it over symmetric limits from negative infinity to positive infinity. Whenever we integrate an odd function over symmetric limits, the integral is equal to 0. So the expectation value of the momentum is 0. Earlier, we have seen that there are only two allowed values of the momentum for this quantum state, h bar k or negative h bar k. The magnitude is well defined, it's h bar k, but we can't be sure about the direction. So what does it mean for the expectation value of the momentum to be 0? It means that both directions are equally probable. The average of the h bar k and negative h bar k is 0. Let's generalize to cases where C1 and C2 are both non-zero, but not necessarily equal. We can see that psi is a linear combination of two eigenfunctions of the momentum. The function e to the ikx is an eigenfunction of the momentum operator with an eigenvalue h bar k. The function e to the negative ikx is an eigenfunction of the momentum operator with eigenvalue negative h bar k. The squares of the absolute values of C1 and C2 tell us the relative probabilities of obtaining h bar k and negative h bar k if we measure the momentum of the particle. The square of the absolute value of C1 divided by the sum of the squares of the absolute values of C1 and C2 is the probability that a measurement would give us h bar k. The square of the absolute value of C2 divided by the sums of the squares of the absolute values of C1 and C2 is the probability that a measurement will give us a negative h bar k. Multiplying the probability of each outcome by the value of the outcome, then adding the results, gives us the expectation value for the momentum. If we choose C1 and C2 so that the squares of the absolute values add up to 1, then we could say that our wave function is normalized with respect to momentum. For stationary states, the wave function, which depends on coordinates and time and typically represented by uppercase psi, can be written as a product of a function of coordinates, shown here as lowercase psi, and a function of time, which is of the form e to the negative iet over h bar. By solving the time-independent Schrodinger equation, we found that for a free particle, lowercase psi is equal to c1 times e to the ikx plus c2 times e to the negative ikx. Let's look at a specific example. We've already seen that if c2 is equal to 0, then we are describing a state where the particle has a momentum of positive h bar k, which means that it is moving to the right. The stationary state wave function can be written as little psi, which is e to the ikx times e to the negative I omega t. Here, omega is equal to e over h bar. Note that we set c1 equal to 1 to normalize the function with respect to momentum. Combining the two exponential factors, we get big psi is equal to e to the I times kx minus omega t. Using Euler's formula, we can rewrite the expression as big psi equals cosine of kx minus omega t plus I times sine of kx minus omega t. We can see the big psi is complex. The real part is cosine kx minus omega t, and the imaginary part is sine kx minus omega t. If we want to plot psi, it would be convenient to plot it versus x for a given t. Then we see how the plot changes as t advances. Here's a plot of the real and imaginary components of the wave function at a given instant. The real part, cosine kx minus omega t, is shown in blue. This cosine function completes one cycle when kx changes by 2 pi. This means that it completes one cycle with x changes by 2 pi over k. Therefore, the wavelength associated with the cosine function is 2 pi over k. The imaginary part, sine kx minus omega t, is shown in orange. This sine function also completes one cycle when x changes by 2 pi over k. Therefore, the wavelength associated with the sine function is also 2 pi over k. Recall that Louis de Broglie hypothesized that there is a wave associated with particles and that the wavelength is h over p. Recall that for the specific stationary wave function we are examining here, we said that the momentum of the particle is positive h bar k. In other words, the particle is moving to the right and the magnitude of the momentum is h bar k. Since h bar is h over 2 pi, it should be easy to show that de Broglie wavelength for a particle in this stationary state is also 2 pi over k. So here, we have derived the expression for the wavelength that de Broglie hypothesized from basic principles. By applying the postulates of quantum mechanics to a free particle, we found the wave function for the particle with momentum h bar k to have a wavelength of 2 pi over k, which is the same wavelength expected from de Broglie's hypothesis. As mentioned earlier, the plot you see here is just a snapshot in time. Let's now take a look at an animation to see what happens as time advances. As time advances, we can see that both real and imaginary parts of the wave function can be described as a wave traveling to the right. If you focus on just one location, you can see that both real and imaginary components of psi oscillate at any given location. At this location, for example, the gray dots track the oscillation of the real component of psi, and the yellow dot tracks the oscillation of the imaginary component. The oscillation is due to omega t in the arguments for the sine and cosine function. Here's what happens if instead of e to the ikx, the time-independent wave function is e to the negative ikx. Recall that this wave function describes a particle with negative momentum, a particle that is moving to the left. This time, the real and imaginary components of the wave function look like traveling waves propagating in the negative x direction. We have seen that for stationary states of a particle in one dimension, the solution to the time-independent Schrödinger equation is given by this expression. For a particle in a box, the boundary conditions, that potential energy goes to infinity at the edges of the box and beyond, lead to restrictions in k, which leads to energy quantization. The stationary states for a particle in a box are said to be bound states. However, for a free particle, we don't have any restrictions, so the energy is not quantized. The stationary states for a free particle are said to be continuum states or free states. In general, we get a continuum state whenever the energy of the particle is greater than the potential energy as x approaches positive infinity, negative infinity, or both. In these cases, the wave function is not normalizable. Instead of going to 0, it just oscillates as x goes to positive infinity, negative infinity, or both. In general, when we're dealing with realistic systems, we will find bound states up to a certain energy level and continuum states at energies higher than that level.